a short delay here. Welcome to our Tech Talk today. We have a case study for Industry 4.0 tool condition monitoring for CNC machines with an illustrious group from the University of South Florida, right here in Tampa. Dr. Nancy Diaz-Elsayed and her students, Sohan, who I don't know, Sohan, I didn't get your last name, pronouncing it, Nagaraj, and Donald McCleeary. Let's see. Next. So I'm, for those of you who don't know, I'm Marilyn Barger. I'm the Senior Education Advisor for Florida Advanced Technological Education Center, part of the Florida Makes Network. And we bring you these series of tech talks every year for the last couple of years to share what's going on in research areas in our universities in Florida. Hopefully we'll have opportunity to share more going forward into next fall. Next. So we have a kind of quick agenda there, just a little bit about FLATE. We'll have our case study presentation and then some time for questions at the end. So for those of you who don't know, FLATE is the Florida Advanced Technological Education Center. We're funded by the National Science Foundation for 16 years, located at Hillsborough Community College to support manufacturing education in our 2-year associate degree programs in the state of Florida. We transitioned to Florida Makes. We're now a partner of the Florida Makes Network and are partially funded by the Florida Department of Education under their Perkins 5 State Leadership Grant Award. But we also have funding from the National Science Foundation and a couple other organizations now to continue the work that we've started under the National Science Foundation's funding. Next. So our vision has pretty much always been to drive Florida's world-class manufacturing workforce education system. And for us, that includes the secondary and post-secondary programs in the state that support manufacturing. And although that's a diverse group, we do focus on the 2-year associate degree and then the pathways going in and out of those 2-year programs onto bigger and better things and starting down in high school. We put our work into these 4 buckets, I'll call them. We work on curriculum reform and development. And in that area, we particularly focus on the frameworks, the Florida frameworks that define standards and benchmarks for these career and technical education programs. Obviously, we support and work with those for manufacturing. We also do outreach and student recruitment. We can't have a good program without students in there. And right now we have a large industry need for workforce in manufacturing. And then we have a big focus on helping students explore manufacturing careers. We also need a good professional development for programs for the educators to have a strong education program. So we provide professional development for our educators, both the high school and the associate level programs. And lastly, we do some work in technician education research, trying to understand the best ways to provide technical education, both in pedagogy and just different ways to meet the needs of all students. Right. Next, please. And so now today we have Dr. Nancy Diaz-Elsayed, as I said, from USF, and her colleagues or her students, I believe they're both students, that work with her in her lab, gonna do our presentation. And let's see, Nancy, I can turn it over to you if you wanna tell us just a little bit about yourself before you get started.
Sure. Thank you, Dr. Barker. So it's a pleasure to meet everybody. I've been at the University of South Florida since about 2014, so quite some time now, but recently transitioned about 1.5 years ago to the Department of Mechanical Engineering. And during that time, course, it was in the midst of the pandemic, so we've been accommodating a lot of changes in education and just our collaboration with manufacturing partners across the state of Florida and then across the nation as well. So very fortunate to work with Dr. Barker and her team at FLATE, as well as the folks at Florida Makes, and we're looking forward to presenting some of the research that we've been conducting in our laboratory in today's webinar.
Great, great, thank you.
Let me pull up my screen. Okay. So the project that we'll be discussing today is on tool condition monitoring. So we'll be presenting an industry 4.0 case study as it relates to CNC machining. Just a quick overview of today's presentation. We'll start off with some of the challenges that were introduced with the COVID-19 pandemic and the increasing interest in adopting smart manufacturing technologies. We'll touch upon sustainability and resilience and what that means for the manufacturing community. And then we'll dive into the CNC machining process and our TCM project, or tool condition monitoring project. At the end, we'll go over the data analysis that was conducted for that work and provide some context about how that data can be used. And so with the pandemic, there were many challenges introduced across the United States and of course across the world. And as consumers, we saw some of these challenges in terms of the shortage of some critical supplies, for example, personal protective equipment early on, especially, and then fluctuating over time as we saw uptick in the rates of COVID-19 cases. So for example, with the United States alone, about 42 million face masks were available in the strategic national stockpile, whereas 3.5 million were needed overall to accommodate our nation's needs. So several challenges, of course, were introduced from a health perspective, increasing our risk to the virus, and from the manufacturing perspective. What does this mean if we have such drastic changes in demand? Is that we're going to have to deal with quite a volatile supply chain. So the materials that are needed to produce products aren't necessarily going to be there when they're needed. For some work related to this effort, we were in touch with the Thomas Net database. They had implemented a COVID-19 response system. And so we could see the demand for different products over time. So in blue here, you can see the inquiries related to masks, so how users are engaging with their COVID-19 response system in blue, and then in this teal color, sanitizers and shielding becoming a bit more popular over time. So this is the 2020 year with the onset of the pandemic starting early on in the year. And so our work deals significantly with sustainability and how we can leverage smart manufacturing technologies in order to inform sustainable decision-making. But what does sustainable development mean? So sustainable development is the development that meets the needs of the present without compromising the ability of future generations to meet their own needs. So when we're not able to meet even current needs, then that introduces quite a bit of a dilemma. Sustainability at large focuses on three different pillars. So we have the social pillar, the environmental pillar, and the economic pillar. Many companies have, for several decades been thinking about profits, cost savings, and their economic growth. Of course, we need economic stability in order to keep our companies in business. So sustainability also introduces the social dimension, which could be in the form of workforce training, improving the standard of living of our employees and our surrounding community, offering equal opportunities to the members of our community, and then also the environmental dimension. So thinking about energy consumption or resource consumption at large, the carbon emissions of our different processes. So sustainability tries to balance these three dimensions: environmental, social, and economic dimensions of sustainability in order to introduce solutions that would provide us with an adequate platform for meeting the needs of current and future generations. We often employ a technique to evaluate the environmental dimension of sustainability called a life cycle assessment. So that would account for the life cycle of our products being produced. So all the way from the material extraction of raw materials such as iron ore, the manufacturing and the processing of these materials, the transportation to our end user, and finally the end of life, which could be the landfilling or recycling in order to recover across any of these phases. So that's a quick overview of sustainability, but what about resilience? So of course, we saw many drastic changes over time in the last couple of years with the coronavirus. So resilience is our ability to recover from or adjust easily from misfortune or change. The supply chain has wreaked quite a bit of havoc over the last couple of years as we're trying to accommodate such drastic changes in demand. We end up seeing what's called the bullwhip effect. So when we're not having adequate supplies within our manufacturing firms, we could be ordering a greater number of goods that overshoots our actual need. And then by the time the inventory actually arrives, we have quite a bit of surplus to take care of. And so we saw some of the issues with the supply chain over the last few months. For example, what was happening in the ports along the coast of California. So here's quite a bit of statistics around the port of Los Angeles and Long Beach. So combined, these ports make up about 40% of all US imports. So when they weren't able to offload the goods, this caused quite a bit of delays downstream as well. So the ports were operating 24/7, and now they're back into normal operations. But it just provides further motivation for improving visibility into our manufacturing systems and into our supply chain overall. That way we can balance efficiency with our ability to respond to changes caused by new events and be immunized from such potentially catastrophic events overall. And so how can we gain that visibility? Over time, there have been many different ages as it relates to industry. So starting off with Industry 1.0 and the mechanization of systems, Industry 2.0, for example, Henry Ford and the assembly line as we were starting to introduce mass production. Industry 3.0, we're introducing elements of automation. And the robotics webinar that we had during the last ET Forum webinar is a great example of the automation robotics that can be implemented therein. In Industry 4.0, which is where we're presently at, and we're even starting to touch upon Industry 5.0, but Industry 4.0 is really around cyber physical systems. So how can we leverage the Internet of Things and the data that could be available for our manufacturing systems in order to make much more informed decisions? And Industry 5.0 starts to bring in the social and so the human element as well as the environmental element as well to increase the sustainability of our industrial sector. So we'll be focusing today's talk on one specific smart manufacturing application, which is tool condition monitoring applied to the CNC machining process. For those of you that may not be familiar with the CNC machine tool and that market, so they're quite ubiquitous. They're used extensively for manufacturing molds, metal products, plastic products, even ceramics. So if you think about how it touches the medical industry, so the molds to make prosthetics or even the prosthetics themselves could be machined. Of course, aviation and aerospace industries, an extensive amount of parts need to be machined with these types of machine tools. So what I'm showing here on the right-hand side is a CNC milling center. Some of the primary components are this controller, so the computer numerical controller. So it was part of that Industry 3.0 era in increasing automation of our manufacturing systems. We have a spindle that holds the cutting tool in order to remove material. And this is the 3-axis milling center. So we have movement along the X, the Y, and then the Z axis, the spindle with the spindle moving up and down, or the frame moving up and down, depending on the configuration of the machine tool. But not only are milling centers able to be computer numerically controlled, but we also have drilling centers, we have lathes, grinding machines, and a host of other types of CNC machine tools that are available to us at our disposal. Talking about the US, in all, the vast majority of manufacturing establishments are small to medium-sized enterprises, so we tend to tailor the solutions that we work on these smaller enterprises, because in that way they can be accessible to our SMEs, but also applied by larger enterprises. So overall, SMEs make up about 89% of the manufacturing establishments in the nation, whereas large enterprises make up about 11% of those establishments. And a SME is generally categorized as being under 500 employees, or by some definitions, under 250 employees. So there are some distinct differences between our SMEs and our multinational enterprises. Typically, SMEs may have lower financial resources available. They might have lower use of advanced manufacturing technologies, but the nature of their product specialization is very high, especially relevant relative to a multinational enterprise, which could have very large breadth and access to these resources on a case-by-case basis. And so in selecting the solutions that make sense for any manufacturer, there are quite a number of challenges to be overcome. Overall, there's a low adoption of smart manufacturing technologies in SMEs. And of course, the pandemic introduced new parameters, for example, the need for remote workforce, the need for greater visibility into our production environment. But in addition to that, in some cases, there can also be a fear of new technologies due to a lack of transparency and inclusion in decision-making. For example, is this new system going to replace my job, or will the investment in the needed upskilling take place as well? And so part of the technologies that we've been investigating have revolved around tool condition monitoring, and how in the context of other technologies, how we can develop a decision-making framework. So towards the end of the presentation, I'll be introducing our decision-making framework for facilitating that process and deciding on which new technology makes the most sense for any institution to invest in. And so with that background, I'd just like to give a quick introduction to our Smart and Sustainable Systems Laboratory. So Sohan and Donald are joining me today as PhD students, and they're the primary students working on the tool condition monitoring project. We have 2 other PhD students, as well as a visiting Fulbright scholar that will be with us for the next 6 months. And the mission of our laboratory is really to develop research that leverages data-driven methods to inform the design of sustainable strategies that are accessible to a broad range of users, to lower impacts to the environment while improving performance. So we're really looking at accessibility, and we'll be introducing some low-cost solutions for tool condition monitoring shortly. But how these technologies can be leveraged in order to also implement sustainable practices across our manufacturing systems. And you will find that actually improving the sustainability of a manufacturing system can also tend to improve their performance as well. So now I'll hand it over to Sohan, who will touch upon the background related to tool condition monitoring and dive into some of the experiments that we've conducted recently.
Thank you for that, Dr. Diaz. Hey, everyone, I'm Sohan Nagaraj, and I'm a PhD student at the Smart and Sustainable Laboratory, and I basically work on tool condition monitoring and tool wear. So that's what I'm going to be talking about today. So statistically speaking, tool wear accounts to almost 20 to 25% of machine downtime. So in a big industry, if you want to have a lot, if you have a lot of CNC machines, and if you have a lot more tools that are worn out, that's going to really affect the flow of the products that are being manufactured in that industry. So to counter that, it's essential to know what the state of the tools are well beforehand, or at least diagnose, there's one diagnostics of what's happening on the tool itself, so that that can be prevented in the near future. But the research is mostly shifting towards prognostics for the near future, because diagnostics is something that's been run over the course of years now for the past decade, and the research scope is shifting towards prognostics. But nevertheless, let me speak to you specifically about what type of toolware we can observe when we're doing machining. So there are three major types of wear that we can see. So one is mechanical wear. Basically, when you're machining a hard workpiece, such as titanium or any other metal which is as hard as titanium, you will have specific tools made for that. Although titanium is really high in strength, you will have tools that are going to be damaged when you're running almost 50 to 100 parts that are being machined. So that's one example of mechanical wear, basically the abrasiveness of the tool touching the workpiece when the machining is happening. And then there's also cutting heat. So that's the reason why machinists use coolant to regulate the temperature. And if there's excessive heat, the chips might melt and stick onto the tool, causing another problem for tool wear. And then there's chemical wear, of course, where the composition of the tool and the composition of the workpiece also play a role at excessive temperatures. So that's why machinists specifically stick to one material type when they're machining tool steel or aluminum or stainless steel. So the workpieces vary in materials as the tools. I'm sorry, let me rephrase that again. So the workpieces, as they vary in materials, the tools also vary in materials, so that the chemical wear is minimal. Next slide.
Sohan, could you go back one slide to ask a quick question? Could you point out on the picture, just to make sure everybody's together with you, the tool in the picture, the tool and the piece that you're working on? So
Yes, that is the tool, and the part that's being machined is the big machine. I mean, the big picture over there, but the tool is the one that's kind of machining it, and you'll see the chips like, falling off the base of the part. So that's the small cylindrical thing that you see is the tool over there, which is machining the part.
Great, thank you.
So these are some examples of toolware, what we found out in some of our experiments in our S3 lab. So these were the first two tools that you see over here are tungsten carbide tools that we use to machine stainless steel and aluminum. So you can see on the first picture on one of the fluids, you can see a black anomaly on the tip of the tool. So that is evidencing tool wear, either due to chemical wear or probably even due to cutting heat. To dive into the specifics of what's going on, when we zoomed in more onto the fluids, we saw that there was material removed on one of the fluids over here on third picture. And then when you go on to the fourth picture, you can actually see a portion of the tool itself and the material on the tool itself being removed. So this is what we characterize as flank wear. And there's also another type of wear that's on the tool, which is known as crater wear. So for flank wear, we basically determine the area of the material removed, but for crater wear, we determine the depth of the crater to determine how much tool wear is going to be on a particular tool. I just wanted to show what tool wear looks like, so everybody has an idea on what tool wear is, and I can go into more specifics later on. So this is what I wanted to show before I dive into any more specifics. Next slide. Yeah, so we get tool wear, but how do we detect tool wear? So there are some tools that we can use to detect tool wear. So researchers have classified the detecting methods into two types. So direct and indirect sensing methods. So your indirect sensing methods usually consist of sensors such as cutting force sensors, power sensors, vibration sensors, which are essentially accelerometers, and also thermal probes and thermal guns. So there has been a lot of research done in this area, and each researcher has his or her own combination to detect tool wear. So sometimes you might have a combination of a vibration sensor and a thermal sensor. Sometimes you might have a combination of cutting force and a thermal sensor. So to find out what combination is the best, or what sensor gives you the most accurate data for tool wear, that's the most pressing question. So like I said, there's the next one is direct sensing methods. And usually they employ optical cameras and vision sensing technologies. So by direct, you mean you can see the tool itself, what's going on the tool. So if there's tool wear, direct sensing methods can be used as a verification step to see if the tool is actually undergoing tool wear, because indirect sensing methods basically go off of the anomalies in the data to analyze tool wear. But however, direct sensing methods can be used to verify what's being shown in an indirect sensing method. So it's optical cameras, microscopes, all of those aid in detecting tool wear. Next slide. So the method, the sensor that we used for our experiment was a accelerometer. So on the right side, you can see that this is the CNC machine, a level LMV 400 CNC machine. It's a smaller CNC machine that you would find compared to like an industry CNC machine, but it serves the purpose for our research. So we placed a accelerometer that's on the right, which is being placed on the vise. And it's placed on the vise, and the accelerometer is connected directly to the PC. Where it transmits data. So the PC acts as a data acquisition and also allows us to configure data. Basically, we can change the frequencies at which we are collecting data depending upon what type of process is being done. So for this process, it was a aluminum 6061 workpiece, and the operation was milling. And the tool that we used was a 2-flute carbide end mill. And we basically ran 5 sets of cutting slots experiments, with each of these slots having a millimeter increment. And the sampling frequency that we did was 200 hertz. And coming to the next part, the vibration analysis, the data what we got was seen on MATLAB, and we used a fast Fourier transform to convert the data from the time domain into a frequency domain. So frequency domain is what the picture you see on the right here is what a frequency domain looks like. So basically it filters out unnecessary signals and just shows you what the frequency peaks look like, which can be used to detect tool wear. And the reason why we do an FFT is because amplitudes and frequencies can be calculated more accurately, and we can see exactly what's going on, and also allows us to identify major frequencies in those data sets. Next slide. Now Donnie is gonna come and step in and talk more about power analysis, because that's his area. So Donnie, you can go ahead.
Thanks, Sohan. Hey everyone. So another set of data, as Sohan said, that we're collecting is power. Basically, just like any kind of electrical device that you use, there's a power consumption aspect to the device. As you can see from the image, again, we have the CNC machine, and it is actually connected through a watt node Modbus to the shop power. The Modbus measures the power coming into the CNC machine as well as the power coming out, and it actually subtracts the two to create an apparent power. And this is the power that is actually consumed by the device. We actually record this data at about 10 hertz using a RS-485 communication system. So there's a serial communication going to the Modbus from the computer. We use a USB dongle to collect the data. And we have we have a custom Python script that we use to display, record, and save the data. And now we're going to have a short presentation of our systems. And if we could just pause the video so I can explain what's going on for a second. So what we have here is on the top right, we have a video of the CNC machine in operation. The spindle at this moment is actually moving. Top left, we have a chart showing the power over time, which is the data that I was discussing in the previous slide. And then the data that Sohan was discussing is here in the bottom, which is the acceleration in G forces. And we're actually measuring acceleration in the X, Y, and Z axes. The Z axis has a acceleration of 1g because of the acceleration of gravity, of Earth gravity. And you can see actually the accelerometer in the top right video as well. It is actually mounted directly to the device right there. So we can go ahead and begin. So as we start, we have some noise in the power data as the spindle is just moving. And then it's moving in to make the first cut. As you can see, the power data actually jumps and creates a plateau during the milling process. As the milling process ends for this first slot, you'll see if you watch the yellow curve, there is some low frequency, high amplitude motion there in the acceleration data that we'll see here in just another moment. There it is. You can see it kind of moving. We also have, if you carefully watch, we also have a lot of really high frequency, low amplitude motion as well. And that's what we're interested in for the acceleration data. We want to see what the acceleration data suggests and shows during the milling process itself. So that's what we want to see. And then after about 150 seconds, it will move to a new slot. Now notice the very first plateau on the power curve is a little bit shorter than the rest of the plateaus. That's because even though we zeroed the Z-axis, it is actually not cutting as much material on the very first cut as opposed to the rest of the cuts. And again, what we're doing in this experiment is we're milling 5 different slots, and each plateau that you see here represents a millimeter of material being removed for each slot. So the very first cut is just slightly shorter than the rest because the material removal rate is not quite as high. Yeah, we can go ahead and skip ahead, and you can see as we move into a milling process that is actually deeper into the width of the material, the plateau rises quite a bit because we have a higher material removal rate now. And in the next slide, we'll see, I'll show you why the material removal rate isn't quite as high in the first pass, the first slot. So I think we're pretty much good here. So yeah, now we'll discuss results. And first we'll discuss the power demand results. If you look at the image in the top right, you actually see the aluminum block that we were cutting. And on the left, you can actually see that first slot that we were discussing that had the lower power plateau. That's slot 1. And then they go slot 1, 2, 3, 4, and 5, as you can see in the power curve chart. And you can also see the plateaus. So as it turns out, the plateaus actually match really well with material removal rate. So that's actually very helpful for us. So throughout this, throughout this process, the blue curve shows the whole raw power data that we were collecting. And almost all of the slot plateaus are between about 30 and 40 watts. If we take the integration of this curve and we measure the cumulative energy absorbed over time or consumed by the device over time, the whole cutting process took about required about 6 watt hours to complete, which is the final value there at the end of the orange curve. So we can measure the energy consumption. And again, the plateaus, where the plateaus are on the power metric, align with material removal rate, but they also align with cutting forces. And it's likely because the cutting forces are higher when you have a higher material removal rate that we get these higher plateaus. So we can move to the next slide. So what we wanted to do is we wanted to take a relatively new tool and compare it to a slightly worn tool that we had in the lab. And what we've done is we've taken just the 3 slots in the center of the experiment of the sample that we were discussing just before. And because the power data there is relatively consistent between slots. And what we're doing is we're just comparing the new versus the old, or the new versus the worn rather. The orange curve shows us the new tool, and the blue curve shows us the worn tool. And we've isolated those plateaus, so we're not getting any noise in the data. And as it turns out, on average, the cutting power required during the process was about 0.57 watts more for the worn tool than the new tool, which could indicate some tool wear. And then I think now we'll hand it back to Sohan to discuss the vibration analysis.
Thank you, Donnie. So circling back to the FFT that I was talking about earlier, the fast Fourier transform. So this is how the fast Fourier transform looks for the data that we got while machining. So on your left, you will see a fast Fourier transform done for data that was gotten off of the new tool. So basically we ran 2 sets of experiments where the machined part was the same, but the tool, one of the tools was brand new and the other one already had some inflicted damage on one of its flutes, though basically on both the flutes because of excessive machining. So we pitted them against each other to see what might actually, what the case might actually be when it comes to frequency analysis. So like I said, the left one shows the FFT for a new tool and the right one shows the FFT for a worn tool. Important, and I'd like to just point out one important thing. So the natural frequency of the spindle was 66 hertz. The reason it's being 66 hertz is because we ran the spindle at 4,000 RPM, and with being in revolutions per second, it's going to be equivalent to almost 66 hertz, the natural frequency. It's good that the accelerometer is capturing that natural frequency. So it shows that the data, what we're getting is what we want to see. Right now, I've highlighted the peaks over here. I mean, when you look at it side by side, you might not be able to see that big of a difference because the amplitudes almost are literally the same when you look at it side by side. But if we can go to the next slide, I'll show you. Okay, this is the picture where we have superimposed both of the FFT peaks, one on top of another. So the orange one shows the orange curve shows the data for the new tool, and the blue curve shows the data for the old tool. So basically, you can see that there are amplitude differences in amplitude. So the new tool has a lesser amplitude for that frequency peak compared to that of the worn tool. One of the reasons being, one of the reasons why you will see an increase in frequency amplitude is because of the excessive noise that might be generated because of a worn tool, because the chips, the chip removal rate and the material removal rate is going to be different because of the profile of the flute itself, the cutting tool flute itself. That might be one of the reasons. And also the exiting of the chips when the material is being cut is also going to be disturbed. So that also can crash into the workpiece at a different frequency range. And there's a bunch of factors that might be affecting what these differences in amplitude look like. But those are some of the major factors that affect changes in amplitude and the frequency. But our hope is to do more analysis like this and go up to a higher frequency range and try and see more anomalies like this, which can evidence tool wear, and probably even in the longer run, just eliminate most of the excess, unnecessary chatter, and just specifically focus only on tool cutting and then look out for anomalies. So that's what I wanted to tell you about the FFT curves. Next slide. And I'll just hand it over to Dr. Diaz again, and she'll continue the rest of the presentation.
Thank you, Sohan. And so, as we're looking at the data, we have run experiments on other types of materials too. And so here, as Sohan and Donnie had mentioned, we're looking at aluminum 6061, which is much stronger than a polyurethane foam. So in comparing the two, the material strength certainly makes a difference as to how much power is being demanded of the machining center when you're removing material, because the cutting forces need to be that much higher. And so the differences between the power data and also the amplitude of the vibrations are expected to be much more pronounced when you have higher strength materials. So overall, the goal for this research is to develop a blueprint to see what the limitations are for different types of sensing methods as they apply to different types of materials being machined. And so a little bit of context for the data and analytics that have been conducted. So how can an operator use this piece of information? So Donnie showed what the power demand for a new versus a worn tool look like, and Sohan had showed what the fast Fourier transform outputs in terms of the vibration of that cutting process. So we can develop a sort of threshold and understand that if we're above this threshold, and we're requiring greater power and we're exhibiting greater vibration than what is expected for that process, then it might be time to switch out that cutting tool. Why is it important to understand when we need to switch out that cutting tool? And so you have a lot of costs incurred. So you can have material that needs to be scrapped if the quality isn't up to par. You have lost time, and you can have losses in terms of the cost of the material itself. So not only the operator time being expended as a labor cost, but also the loss of the material itself. And so just to give you a range, so some commonly machined materials are aluminum alloys, titanium alloys. At the very high end in terms of the price of the material is Inconel. So that's used very often in aviation and aerospace part manufacturing. We also show here for context some ceramics like alumina, concrete, and the price of some thermoplastics like polyethylene and PLA. So often what you could be using for 3D printing, for example, would be a PLA, which is about $3.20 per kilogram. So in these defense sectors where we're machining parts for the aerospace, aviation, transportation industry, the parts that we are using are generally very expensive because they have to be high functioning materials. So if you have a tool path that say takes 16 hours, you're machining this very large work piece, and then you find out at the end of that run that your cutting tool broke, or that it was too worn to lead to a good enough finish, then you're scrapping that material, and that could be thousands of dollars just for one work piece. Hopefully you catch it in time and you haven't produced 5 of those same parts in an automated run, but surely we can implement remote monitoring techniques such as tool condition monitoring in order to inform when those tool changes are needed. And to give some perspective in industry, how those changes could be determined is by visual inspection. So say you have a part that you're machining and the quality is not up to par, or you have too much surface roughness, the dimensions are off. These are all certainly cases that could be a result of tool wear. And oftentimes in visiting some manufacturers here in the Tampa Bay, the operators will just do a visual inspection of the cutting tool and then deem when it's necessary to switch out that cutting tool. So there are certainly opportunities for leveraging some smart manufacturing technologies to save time and money, and then reduce any waste within our manufacturing facilities. And so we gave one example of an Industry 4.0 technology, namely tool condition monitoring. In our laboratory, we've worked on other applications of smart manufacturing technology. So we have some work with 3D printers. We have also done modeling of the ambient conditions within the machining environment using computational fluid dynamics. And then so as a manufacturer, if you think about making new investment decisions and what technology makes the most sense, we've developed a framework to help facilitate that decision-making process. So you can consider, for example, a multitude of criteria related to performance, related to quality, maintenance, sustainability, cost, and of course, safety, which could be of utmost importance to a company in order to deem what would make the most sense from an investment standpoint for your institution to invest in. So in another case study, we evaluated tool condition monitoring relative to conventional machining, the modeling of ambient conditions, and combining these two smart manufacturing applications for a more advanced state. And so we implemented TOPSIS, the technique for order of preference by similarity to ideal solution. And so with this technique, you could essentially compare the desirability of every solution relative to the list of criteria that I had mentioned previously. And so we use a fuzzy TOPSIS methodology. I won't dive too much into this methodology because that could be its own tech talk in and of its own. But with this technique, we're able to rank the preferences of a number of stakeholders for an institution. And so here we can see that what was highest ranked was the safety of personnel, followed by cost, followed by the ability to predict quality. And so we rank our list of criteria, and the number of criteria that can be considered can be as little as 5 to, in our case, we were using 10 different criteria to analyze. And then we saw that machining with TCM and understanding the ambient conditions to inform more precision manufacturing ended up ranking the most for our laboratory. And so in all, with the development of these technologies, we're looking at increasing this accessibility to these smart manufacturing approaches so that manufacturers can implement them on the factory floor with ease. And with this framework, more specifically, facilitate collaboration amongst key stakeholders. And so we have a multitude of organizations and people to thank that have supported this work: the Alfred P. Sloan Foundation, the Social Science Research Council, and our College of Engineering, who have provided some financial support for this work. Of course, the feedback from the members of our S3 laboratory and the personnel at the Nanotechnology Research and Education Center that have facilitated the taking of the images with their digital microscopes. So thank you. I think there might be some questions in the chat, so we'll have some time for questions.
Thank you, Nancy. That was really interesting. There was a question early on about, so I'll start at the beginning, about some of the charts you had, I think in those first sustainability slides. Someone was asking if those charts were available. I guess that was, is there a reference on those slides that they can get to if they get the slide deck?
Yes, and I can even share the paper that was referenced as well. So I would be happy to. And do we already have the slides distributed?
Did they get posted? We had some security issues of uploading them. Did they get?
I can share the box link, and then so everybody would have access to those the slide deck in that form.
That would be great. So for some reason, I think with this latest update that happened this week, there was some security issues.
Yeah, no problem.
For that. So that would be great. So that was one question. And Dr. Gilbert is here with me. He's got a question.
Yes, I do. I'd like to just get a little bit of information relative to the sensor interface. You used the RS serial communication port, and it has a separate data transmission bit. Did you include that in your protocol, and why did you select the language that you selected for your interface?
Oh, great question. So I could start off and then Donnie can chime in. And so it was a matter of communicating with the Modbus system. And so we were looking for, in prior work, we had used the MT Connect protocol to facilitate the time synchronization of a vast array of data sets. But here we were just looking for power. So we were looking for a feasible solution to communicate with the watt node Modbus power meter. And so this was the dongle that was used for the RS 485 communication system was actually relatively inexpensive. So we're looking for low cost solutions, and we're trying to see how well that would work for our TCM experiments. Donnie, did you have any other information to add?
Yeah, you mentioned something about a separate data stream. Could you ask? Could you repeat the question, please?
Okay, when you're using RS-232 communications, there are several bits in the protocol that allow options, and one of them is data send, data receive.
Mhm.
Did you use that option?
Data send and receive.
Yes.
So in the RS-485 communication, there was a manual on it. There are different registries that you can query and get data from. I did not see an option for data send and receive. From what I understand, the way that the Modbus will continue.
Okay, thank you. Let's jump to the other question. Why did you pick the language that you picked?
Are you talking about the Python script, or are you talking about RS-485?
I got the impression you used Python as the interface language between your sensors or data transmission to your computer.
Yeah. So the first issue is that there was no software option that we could use to actually collect the data. There was a freeware software that we used originally just for testing. That was all it did was show us like a live data stream, but it wouldn't really record anything. So the reason we used Python was because we needed a way to be able to query the Modbus through RS-485 and collect the data.
Okay, thank you. There is the data send receive separate wire or bit in the RS-485 communication protocol. It is often used for that last task, and I was trying to focus on if you actually did that or not. Thank you.
Okay, I'll ask Daniela, who's looking at the chat, or Teresa, is there anything else in the chat?
No,
Not right now.
no questions. So this is the opportunity. If anyone has more questions, have a question, please text or write in the chat box.
But in the meantime, I have a question myself, since my background's in environmental engineering and water treatment specifically, and wastewater treatment. So I was interested in what the project was using that in that discipline area that you worked on. Can you give a high level overview?
Oh, sure. So we were looking at different resource recovery techniques. So how can we recover resources from wastewater, and what would be the sustainability impacts related to that? So we were considering from wastewater, the recovery of water, so water reclamation, your typical purple pipelines, but beyond that, indirect potable reuse, energy recovery, all different forms, thermal, incineration, et cetera, from biosolids, and then also nutrient recovery. So from fertigation to the concentration of biosolids to facilitate nutrient recovery for land applications. And so there were a number of different case studies that were conducted to that, from the household scale all the way up to the county scale. Eventually, we built a web-based tool to facilitate the design of water reclamation systems. So we worked with Hillsborough County, and we consider the technologies that could be implemented in the state of Florida, such that if you have feasible locations for new or the opportunity to renovate existing wastewater treatment plants, where would they be optimally located, depending on how your population is spread out within that community?
Ah, interesting. Thanks for that. Was there a particular one for near waterways, like near our rivers in Florida? That was really good. I'm just trying to find a geographic idea. Something that might.
Oh, of course. So in the recommendation, I believe we ended up expanding one of their large wastewater treatment plants, it being the recommendation with the BART info system. So to facilitate better nutrient management. And so we looked at the Falkenberg wastewater treatment plant, amongst others, but I'd be happy to send you that paper too, Marilyn. And I will, just for everyone's reference, I don't think they're included in the slides, but I'll add my email address. Anybody would like to touch base.
They are not. So. Thank you for that. And go to the next slide real quickly. We'll point out the, oops, there's one of the resources there and the link to her lab. So I believe the email would be there. Okay, Teresa, next. And lastly, we have 2 more scheduled webinars for Tech Talks, and one is coming up in February with Dr. Wu from UCF, and he'll be doing applications of machine learning and some smart manufacturing, and he's got a really interesting take on that. And lastly, we are going to have a little panel of the 3 Tech Talks that we had this year with Gloria Weems and Nancy and Dr. Wu in April, just to kind of sum things up and talk about advanced manufacturing going forward with a little review of their talks and see what they see coming into the future. The registration's not set up for that yet, but it will be soon and will be on these websites that you see below. And I guess with that, I'm going to close up. Any final words, anyone can say? Last questions, we have 1 minute. If not, we'll just say thanks a lot for the team from the University of South Florida Mechanical Engineering Department. And see you all next time. Have a great rest of your day.